because it's been a long time, right? I missed Thursday, we missed Tuesday because of breaks. It's been a long time since we've been together. So we're talking in chapter 5 about probability. And I want you guys to help me. So when we talk about probability is always between 0 and 1. It's expressed as a percentage. It can be expressed as a ratio, like 1 in a million, 1 in 5, something to that effect. And what we do first is we start out with a random experiment. Give me an example of a random experiment. Give me an example of a random experiment. Give me one random experiment you can conduct right now. Kyle, come on. Okay. I guess, yeah. Because you either did your homework or you didn't do your homework. That's the sample space, right? Actually, I think I had different. I said you did your homework, you did it halfway. So there's like 3 outcomes, right? You get a 0, you get a 3, or you get a 5, right? That is a random experiment, right? When we have a random experiment, flipping a coin, playing a game, what we try to do is in set notation, let's reverse set, we say these are the possible outcomes. So you can get a 0, you can get a 3, or you can get a 5. Those are the possible outcomes when I check homework. Very good. You play a game, you flip a coin, heads or tails, win, lose, tie. Your investment goes up, your investment goes down, your investment stays the same. These are all examples of random experiments. What do we call the things in the sample space? What do we call like 0, 3, 5? Those are called what? What's the word we use to define those? Those are outcomes, right? And if we think about it, if it's one outcome, we call that a simple event. And if it's more than one outcome, like getting a 3 or higher, we call that an event. And a couple rules that go with probability. Probability is always between 0 and 1. And if we sum up all the probabilities, they should sum to what? They should sum to 1. Okay, so those are some rules, always true of probabilities. And we use some words when we talked about a sample space. The first one was we said the sample space is mutually exclusive. Like the outcomes in a sample space are mutually exclusive. What does that mean? What does the mutually exclusive mean? Rachel? Right, I either get a 0 or a 3. You can't get a 0 and a 3, right? They're kind of, if we get one, the other one is excluded, mutually exclusive. And the sample space is also exhaustive. What does exhaustive mean? Mr. Boyd? Okay, very good. It includes all possible outcomes. So, Mr. Boyd, I'm going to give you a point back for that answer, okay? Yeah. So, Mr. Boyd earned a point back. All right, so that's true. And when we assign probability, there's 3 ways we can assign probabilities to outcomes. How do we do that? Boy, you're going to work your way back up. Go ahead, Mr. Boyd. All right, so the 3 things are the classical approach, the relative frequency approach, and the subjective approach. So let's say this, okay? Let's talk about the game tomorrow night against Duquesne. If I look back and I said the last 10 times we played Duquesne, we won 3 times. So there's a 30% chance that we win because historically speaking, we've won 3 out of 10 games against Duquesne. What approach would I be using, Mr. Boyd? It is, because I'm looking back historically. Very good, okay? If I said this, I said, the hell with playing the game, we like each other, we're just going to go to the middle of the field and flip a coin, and whoever wins the coin flip, the game is over. So I'm saying that St. Francis has a 50% chance of winning that game. It would be what, Mr. Boyd? It would be, because if I have the same number of outcomes, right, and I say, what's the odds that one outcome happens? Well, 1 out of 2, 50%. And further, if I say, all right, based on my expert knowledge of the games, the teams, and I saw that we blew out a Bryant this weekend, and I think Duquesne's a little bit cocky right now. I say the odds that we win, it's a home game, it's homecoming, big stuff, is 80%. That's based on my personal opinion. What would that be? All right, so Mr. Boyd, you're whole. So subjective approach, very good. All right, so those are some of the conceptual things that we learned. Also, as part of that, okay, we also talked about, probability itself is pretty easy, but when we start combining events, that's kind of where things get a little more difficult. So we talked, and this slide probably does it justice best, we talked about the complement of an event. What's the complement of an event? Someone with a 0, you can bring yourself up. What's the complement of an event? Kyle?
I guess an event that happens because of an event.
No. Complement of an event. Come on. Yes. You got to read a slide, Timmy. Come on, give it to me in your words.
All right.
Give it to me in your words. What's the complement of a win?
A loss.
A loss is right. The opposite, right? So the complement of flipping a coin and getting tails is the opposite of that. Okay. So the opposite. So when we talk about a complement of an event, we use a superscript C. So the odds of the complement of an event is 1 minus the probability of that event occurring. So if I said the odds of us winning this weekend is 80%, the odds of us losing is 20%. Does that make sense? It has to add to 1. We also talked about intersection of events. What one word kind of comprises the intersection of events? What one word comprises the intersection of events? Very good. And, right? That means this event occurs and this event occurs, right? Both happen at the same time. So if we look at it as a Venn diagram, it's where both A and B are true. Where both A and B are true, where there's overlap. How about a union of events? What's the word that means union? I think you're whole, aren't you? I think you're whole, aren't you? Get someone else. Boy, you're whole too. Give someone else a chance to redeem himself. Rachel, you did your homework. Come on. Or, right. Or is a union, right? That is A or B occurs. So we're going to talk about situations like that. And now what we really spent some time on, okay, was we talked about conditional probability. Okay, so that's kind of where I want to start. We talked about dependent and independent events. So when we talk about independent and dependent events, we have to introduce this concept of conditional probability. So we can talk about the probability of A occurring given that B is known. This is conditional probability. The probability of A occurring given that B is known. The odds that you graduate from college given that you're a male. Okay, is that different than overall graduation rate? It is. Okay, there's a relationship there. That you're a student athlete, does that change your graduation? It does. So those would be dependent events. The way we figure out conditional probabilities is we say the probability A given B is equal to the join of the two divided by the probability of the second, right? The probability of A given B, the A occurring given that B occurred, is the join of the two divided by the probability of the second or B occurring. All right. What we used to kind of teach this was something called joint probability table. So let's do one of the homework assignments, or maybe one or two, so that we can understand this. So this was section 5.2, 7, 9, 10. Let's take a look at some of those. Did we do number 7? Was that one I signed? Yes, sir. Yeah, I checked the homework, but you have to be present for that check. So, yeah, sorry. So let's look at number 7. Okay, we have a joint probability table. It says the following table lists the probabilities of unemployed females and males and their educational attainment. Okay, so we have female, male, and we have their different attainments. So let's take that and build, well, we have a joint probability table. So let's figure out what it's looking for. So I'm going to replicate that table. And we're going to say less than high school, some college, and college and university. That was awful, John. Let's do it again. Less than high school, high school, some college, and college and university, and we have two things. We have female and male. Okay, so 0.077, 0.154, 0.141, 0.092, 0.110, 0.201, 0.129, 0.096. All right. So the first thing I do, this is a joint probability table. The first thing I do when I have a joint probability table is do what? What's my first step? Yeah, I want to add down the columns and across the rows. So if I add the female column, let me do that first. So 77 plus 154 plus 141 plus 92. I think I get 0.464. Is that what you guys got? Okay. Let's add the male column. 110 plus 201 plus 129 plus 96 gives me 0.536. That should add to 1, and it does. Okay? Let's add the less than high school column. 110 plus 77 gives me 180.187. 201 plus 154 gives me 0.355. 141 plus 129 gives me 0.270. And this gives me 0.188. Okay, so if I do the math, did I screw something up there? It looks like I screwed something up. What did I screw up? Did I? No, I didn't. I don't think I did. Okay, so that does add to 1. All right. So let's see what it's asking us for. Okay. Let me just, I'll tell you what, I'm just going to ask you some things. So what's the odds that an unemployed person, so these are all unemployed people, is female? What's the odds that an unemployed person is female? What's the odds overall that a person is female in this table? I would look to the margin, I would say 46%, okay? What's the odds that an unemployed person left high school? So this whole table represents unemployed people, so unemployed person left high school. Where would I look? Very good. I look to the margin. For overall probabilities, I look to the margins, yes? If I said, what's the odds that an unemployed person left high school and is male? So you heard that important word in there, and. What do I have to do now? Delando? Right, you have to look where they intersect, right? And intersect, it's 11%, okay? So let's do this, all right? Let's say the probability of, so we want to know if there's a relationship here between gender and, and their education status, okay? So overall, the probability of college and university is 0.188, right? Overall, the probability that someone went to college or university, an unemployed person, is 18%. What's the odds that someone went to college and university given that they are female? How do we figure that out? How do we figure that out? So that's a conditional probability, that they went to college or university given that they're female. What will we have to do? And I'm pointing up to the board because that is the formula we want to use. What would we do? Okay, we have to join the two first, right? So the probability of CU and F is the probability of CU and F. We have to join the two, divided by the probability of F overall. So where do those two things join? CU and F join at 0.092, that's the numerator. Probability of F, you guys already told me, is 0.464. So let's see. 92 divided by 464 gives me 0.0193, or actually 4 if I round right. Okay, 0.0194. So at this point, I can tell you if these events are independent or dependent. Here's why. The probability that an unemployed person went to college, got a degree, is 18.8%. The the probability that that we know that they're a female, that they went to college and university, the probability goes up to, or goes down to, 0.198, I'm sorry, 0.198. Okay. So overall, the odds that someone went to college or university is 0.18. If we know they're a female, that goes up to 0.198. So because it's different, what do we call those events? Because they're different, we call what rate? Dependent. If the rate didn't change, if the conditional probability was the same, we would call them independent events. Because it's different, we know it's dependent events. We only have to check one, right? As soon as one conditional probability is different than the overall probability, we know these events are dependent. Okay? Let's do another one. Let's do, did we do number 6? Did we do number 6 maybe in class? Did I give you 6 for homework? Okay. Let's do number 6. Okay. 6 says, a department store analyzed its most recent sales and determined the relationship between the way the customer paid for the item and the price category of the item. The joint probabilities in the following table were calculated. So I'm going to recreate this in a joint probability table on a piece of paper here. I'm going to say under 20, 20 to 100, 100 plus. We're going to say cash, credit card, debit card. And I'm going to fill in the probabilities. 0.09, 0.05, 0.03, 0.03, 0.21, 0.23, 0.04, 0.18, 0.14. Okay, that's my joint probability table. First thing I do, what? When I get a joint probability table is add down the columns and across the rows. So I'm going to do that. So this would be 17%. This would be 47%. This would be 36%. That looks good. This would be 16%. Be 44%, I believe, and that is 40%. So 1.0, they both add to 1.0, I'm good. Okay. Now let's follow this one and give them exactly what they want. So it says, what proportion of purchases was paid by debit card? So what am I looking for here? Sometimes students struggle with this. What proportion of all purchases was paid with debit card? All I'm looking for is the probability that a debit card was used, the probability of DC. What is the probability of debit card? How do I find that? Marcus, how would I find that? The probability that a debit card was used overall, that's all I care about. Where do I need to look? Right in the margin, right? 36% is the probability that a debit card was used. That's number A, 36%. Very good. It says, find the probability that a credit card purchase was over $100. That's A. That's B, I'm sorry. So one thing I want you to note in that sentence, find the probability that a credit card purchase was over $100. Do you see the word and anywhere in that sentence? No. So we're not talking about an intersection here. This is a conditional probability, okay? This is sometimes difficult to say, go from that word to a conditional probability. We want to know the probability of what given what is known. Find the probability that a credit card purchase was over $100. What do we know? What is the given part? I always start with the given part. What do we know about this subset? Find the probability that a credit card purchase was over $100. So what's the known part? Very good. That's the given part. Find the probability that a credit card purchase, of the credit card purchase, given a credit card purchase, we're asking the question, what's the probability it was over $100? So this is what this one looks like, right? We're trying to figure out the probability it was over $100 given that it was a credit card purchase. Does this make sense? So what do? We join the two, divided by the probability of the second. Okay, let's see. The joint of the two, 100 and credit card, they join at, God bless you, they join at 23%, so that's my numerator. The probability of a credit card purchase, well, I need to go to the margin, 0.47. So now we have 23% divided by 47%, and we get 0.489 or 48.9%. At this point, I can tell you if these events are independent or dependent. What do I need to compare this value to figure out if it's independent or dependent? If these events are independent or dependent. Total what? No. What's the other one, Mr. Boyd? Very good. I know the probability that a purchase was over $100 is what? 40%. If we know a credit card was used, the probability that was over $100 goes up to 48%. So is there a relationship between the way people purchase something, the method they use, and the amount of the purchase? What would you say? There is for sure, right? There is, because they're different. That's dependent, right? Because they're not equal. Because 40% does not equal 48.9%. The overall probability of it being over $100 is 40%. If we know that a credit card was used, it goes up to 49%. Just for kicks, let's figure this out. What's the probability that an item given a credit card was used, what's the probability the item was under $20? Let's figure that one out. We know a credit card was used. What's the probability the item was under $20? What do we need to do in the numerator? We know. What do we need to do in the numerator? What do we need to do in the numerator? Join them, right? So let's see, where they join. 20 and credit card. That's a numerator of 3%, right? That's where they join, 20 and credit card. Divided overall by what? Percentage of credit card, which is 47%. Okay, so 3% divided by 47 gives me 0.064%. Does that surprise you that it's different than 40%? Well, I guess I should compare it to this. What's the probability that an item overall is less than 20%, $20? 16. What's the probability it's less than $20 given a credit card was used? It goes down to 6%. Once one is unequal, they're all going to be unequal. Does that make sense? If there's a relationship, they're all going to be different. Yes, no? How about number 10? Let's do number 10. Last one. This is kind of it's not really an aging schedule, but you guys know what an aging schedule is? Anyone in accounting here know what an aging schedule is? Someone say yes? You know what an aging schedule is? All right. How about accounts receivable, right? You know what accounts receivable are, yes? Yes, okay. So I'm owed money, yes? So when I'm owed money, what do you think is the determining factor, one of the determining factors on if I'm going to get it back? All right, let's meet. Mark I borrowed $20 from Mark, right? Okay. And you're thinking, Nico's a good guy. He's going to give me that $20 back, right? Yeah. You think I'll give you $20 back? Okay. So it goes a week, and I see you, and it's an awkward kind of stance, right? And I don't give you the $20, and then, it goes like a month. We see each other again, and it's even more awkward. I'm talking about other things, and it goes 3 months. What's happening to you as the time goes? What are you thinking about the likelihood that I'm going to pay you back? It's less and less. So here's what firms do. Like say they're all owed total $1 million, right? Say they're owed total $1 million. And it looks like this. Under 30 days, I don't know, there's $900,000. They're less than 30 days. Between 30 and 60, maybe we have 100,000. And between 60 and 90, maybe we have 50,000. And 90 plus, we have another 50,000. So that totals $1 million. What firms can do is they know they're not going to get all that $1 million, are they? They're not. They just know historically people don't pay you sometimes, right? But they know historically using relative frequency that if funds are in this category, less than 30 days, we typically collect, I don't know, let's say 95% of that money. Usually 95% of that gets paid back. If it's in the 30 to 60 day range, maybe we get 80% of that money. If it's in the 60 to 90 days, hey, maybe it's 50%. And if it goes down to 90 plus, if it's over 3 months due, maybe only 25% of the time do we ever get that money. Does that make sense? So why would a firm do that? Why would a firm do that? Why would an organization age their accounts receivable? Yes, Kyle.
I guess to account for like loss.
Yeah, they want to know. They know they're not going to get all $1 million, right? They want to know about how much do I expect to get from that $1 million I'm owed. I know I'm not going to get it all, right? So I'm going to get 95% of this. I'm going to get 80% of this. I'm going to get 50% of this and 25% of that, right? And then after it goes past 90 days, you know what they do a lot of times? Or 120 days, it depends what the firm is. But what do they do then? A couple things. Tony, what do they do? Okay, they say they do what they call charge it off. They say, we're never going to see that money, so I'll sell that debt to a collection agency, typically for like pennies on the dollar. Like I say, you know, Mark, I owe you 20 bucks, right? You're saying, I'll transfer that debt to Tony, right? Tony gives you $1, and Tony then tries to collect the 20 bucks off me. Maybe he uses he calls me, you know what I mean? He uses hardcore techniques, and maybe he threatens to beat me up, something like that, right? So that's what collection agencies do. They buy debt for pennies on the dollar, and then they work like how to collect it, right? That's why once it gets turned over to collection agency, that's their MO. That's what they do, right? So that's why they're calling people. Does that make sense? So that's how business works. All right. So let's look at this example. It says, a firm has classified its customers in 2 ways, according to whether the account is overdue and whether the account is new, less than 12 months. Is that blurry? Okay, that's better. And now, so the firm's records provide the input for the following table of joint probabilities. So let's do this one. Okay, so I'm going to take a piece of paper. This one should be easy. We're saying new, old, overdue, not overdue. And we have 6, 52, 13, 29. First thing I do is what? I'm going to add down the columns. 58, this is going to be 42, 19, 81. Those add to 1. We're good. Okay. So let's see what it's looking for. It says one account is randomly selected. If the account is overdue, what is the probability that it is new? Okay. So if the account is overdue, what is the probability that it is new? Do you see the word "and" in there at all? Okay, so we're not talking about a joint probability. Radio or something? Okay. We're not talking about a joint probability. We're talking about a conditional probability. So help me determine what is the given part. If the account is overdue, what is the probability it is new? What is the part that we know? That goes second. The thing we're looking for the probability of goes first. What is known? Evan? Right, we know it's overdue. The account is overdue. Given the subset of overdue, we're looking for the probability it is new. So we're looking for new given the probability that it is overdue. Overdue is the known part, the subset. Does this make sense? So what do? We join the two, new and overdue, divided by the probability of overdue. So the join of the two, let's see, where does new and overdue join? Looks like that is 6%, right? They join at 6%. The probability of overdue overall is 58%. So we have 6% divided by 58%, which gives me 10.3%. What do I need to compare that number to tell if these things are independent or dependent? The probability that an account is new, given that we know it's overdue, is 10.3%. What do we need to compare that to tell if these events are independent or dependent? Very good. The probability of the first one, new overall. What's the probability? If we don't know anything, if nothing is given, what's the probability an account is new overall? 19%. Because they're different, what do we say? These events are dependent. Does this make sense? Let's do number B, or letter B. Letter B says, if the account is new, what is the probability it is overdue? So that's different, right? What do we know about this account? It is new. We're looking for the probability of overdue. So once again, we're going to join the two. So my numerator doesn't change. It's still 6%. But now I'm saying of the subset of new, so the probability of new is 19%. So we have 6% divided by 19%. That gives me 31.6%. I would want to compare that to overdue. Overdue overall is 58%, right? But if we know the account's new, the odds that it's overdue goes down to 32%. They're related. There's dependence. As soon as we prove one is not equal, they're all going to be not equal, right? If they're dependent, they change. They affect each other. Yes? Does this make sense? Yes? You guys can do this? Any questions on any of the other homework? All right, we're going to move on then. All right, we're going to move on to the next section, and it's called probability rules and trees. Okay? And we already did one of these at least. Okay? We already did the complement rule, but let's introduce you to all of them. So we also want, we understand joint probability, we understand conditional probability, but we also need some other tools to help us understand some other events that we're going to encounter in the world of probability. And the first one is something called the complement rule. And I think we already went through this. The complement of event is the opposite of that event occurring, denoted with a superscript C. So the complement rule is just a form that says the probability of A complement is 1 minus the probability of A. And I think that makes sense. If the probability of us winning is 70%, 1 minus 70% is 30%. That's the probability of us not winning. Okay? Now I'm going to skip the multiplication rule for a second because I think it makes sense when we talk about trees. Okay, so let's come back to the multiplication rule. And let's move to something called the addition rule. The addition rule is used for unions. And it looks like this. The probability of A or B, A occurring or B occurring, is equal to the probability of A plus the probability of B minus the join of the two. Now, this makes sense. The probability of A or B is the probability of A plus the probability of B. But why do we subtract out the joint of the two? I want you to think about why we subtract out the joint of the two. Because A or B means if A is true, we want to count it. If B is true, we want to count it. But why do we subtract out the joint of the two? Daniel. Very good. If you think about it, if I say the probability of A, envision it, I'm counting this circle, right? Plus the probability of B, I'm counting this circle. I kind of double dipped, right? What area did I double dip? What did I count twice? The intersection, right? So if I counted it twice, how do I get rid of it? I subtract it out once. Does that make sense? So that's what the addition rule says. The probability of A or B is equal to the probability of A plus the probability of B minus the joint of the two. Let's look at an example of this. Let's do a problem. I think that makes the most sense. So in a large city, two newspapers are published, the Sun and the Post. The circulation department reports that 22% of the city's households have a subscription to the Sun. So the probability of someone subscribing to the Sun overall is 22%. They also report that 35% subscribe to the Post, and there are some well-read readers, probability of P and S, 6% subscribe to both. It wants to know what proportion of all the city's households read a paper, right? The Sun or the Post. We want the probability of S or P, that one of them is true, that they get a paper. What does the addition rule say we should do to calculate this out? What do we need to do? Pretty simple. What do we need to do? Very good. The probability of Sun plus the probability of Post minus the probability of the joint of the two. Because when we counted this one, we double dipped these people, right? That's 6%. So 22% plus 35% minus 6%. We have 47%. 57% minus 6, that's 51% of the city's households subscribe to the Sun or the Post. Does that make sense? Okay. I'm going to kind of go off topic here, off slides anyways, and I want to talk about probability trees. Probability trees are a way for us to visualize a series of events. So let's say this. Let's try to, I don't know, let's take an example. So in a room, I have, let's say I have 6 males, and this probably isn't politically correct, but 4 females. I shouldn't have done that, but I don't know you know those gender symbols? I don't know those. You know what I'm talking about? That has an arrow, and you guys know what I mean? Which one's which? You know? Let's do that. Let's do. That's not politically correct. I think this is the male, isn't it?
Yeah.
And is this the female? All right, we'll do that. Because if I see that on like a bathroom, I'm always like, shit. I'm gonna have to wait until someone else goes in, or I can peek into your urinal and then I go in. But all right, so we'll say there's 6 males and 4 females in a group. Okay. I want to know the odds that if I randomly do 2 selections, right? I pick twice. What's the odds that I pick 2 males? You know what I'm saying? Like I don't put it, and now I have 9 people. I pick again. What's the odds that I randomly select 2 males? How would you do that? Anyone? Tony, do you know? You have an idea? Did you raise your hand or did you just brush your hair up? Sorry. Okay, let's envision the first thing. I think this is where probability trees really help us out. For the first pick, there's only 2 outcomes. What are the 2 outcomes? And we're going to draw it as a branch. What are the 2 outcomes for the first pick? I can choose what? Okay? The odds that I choose a male on the first pick is what? 6 out of what, Mr. Boyd? 6 out of 10. Very good. The odds that I choose a female on the first pick is what? 4 out of 10. Okay, I want you to note something. That split, the branch of the tree, 4 tenths plus 6 tenths adds to 10 tenths or 1 or 100%, right? And if there were 3 genders in here, right, we'd have to have 3 branches to that tree. You know, like alien, male, female, we'd have to have 3 branches. But we don't. Now, this was the first pick. So the problem comes in is we have to try to envision the second. So if I'm at this part in the tree, what has already happened? If I get to here, what has already happened? My total went down, and who did I remove from the group? One person, and that person happened to be a? Well, if I'm at this point in the tree, Mr. Boyd, given that this just occurred, we know that we removed what? We removed a male. So if we get to there, we know we have 5 males and 4 females. So when I do that second pick, after I've chosen the male, what is the odds that I choose a male given that I just chose a male? What are the odds that I choose a male given I just chose a male? So we're down to 9 people, 5 males. What's the odds that I choose a male given I just chose a male? Very good. Does that make sense? What's the odds that I choose a female given that I just chose a male? 4 ninths. I want you to know 4 ninths and 5 ninths adds to 9 ninths or 1 or 100%. Very good. Let's go back. Okay. If I'm at this point in the tree, what has just occurred? If I'm at this point in my path, what has just occurred? I picked a female, right? So now I'm still down to 9, 6 males and 3 females. So I'm going to draw a branch here and say, the odds that I choose a male, given that I just chose a female, is what? 6 out of 9. The odds that I choose a female, given that I just chose a female, is 3 out of 9. Okay? And if we pick 2 people at random, think about it. That's what I've done here. There are really 4 combinations that can happen, right? Male, 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 female, 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 male. 4 combinations. How many ends does my probability tree have? 4. These are the 4 combinations. If I go this way, that's male, and I chose a male. If I go this way, that's a male and a female. If I take this path, that's a female and a male. And if I choose this path, that's female and female. Okay, so I've kind of visualized this, but I haven't figured out the probability. Well, you remember that rule I skipped over? That rule I skipped over was called the multiplication rule. And the multiplication rule looks like this. It says if I want to figure out the probability of A and B occurring, 2 events occurring, I need to multiply the odds of one occurring alone times the odds of the other one occurring, given that that has just occurred. The probability of A and B is the probability of A given B times the probability of B, or the probability of A and B is the probability of B given A times the probability of A. All it really means, and I think this is the best way to, and I have to do this, the best way to visualize this, if I want to figure out the odds of choosing a male and a male, all I have to do is multiply along that path. 6 tenths times 5 ninths, that gives me 30 90ths, which is 1/3 or 33.3%. If I want the odds of choosing a male and then a female, once again, multiply 6 tenths times 4 ninths, that's 24 90ths. 24 90ths, I'm having trouble doing that in my head right now, but 24 90ths is, let's see, 24 divided by 90 gives me 26.67%. The odds of choosing a female and then a male is 4/10 times 6/9. That's also 24/90, or 26.67%. And the odds of choosing a female and a female is 12/90. 12/90 is 13.33%. Guess what happens if I add up those four values? What should those add up to? 1 or 100%. Now I have that information. What's the odds that I choose two males? What can you tell me? That I randomly select two males? 33%. The odds that I select two females? 13%. What's the odds that I get, I don't care what the order is, what's the odds that I end up with a male and a female? I don't care which way I selected them, what's the odds I end up with a couple? What would I have to do to get the odds of ending up with a couple? I end up with a couple here and a couple here. To find the probability of both of those, I add them up, and I think I get like 53.33%. Does that make sense? Okay. Let's have you guys do one. Okay, let's have you guys do one of your books. So, number 11 is a good one. So here's what I want you to do for number 11. Define the events, draw the tree, and then figure out what they're looking for. Define the events. What are the events that are occurring here? I can tell you what they are. Winning the first contract, losing the first contract. Winning the second contract, losing the second contract. Define those events, draw the tree, and then figure out what they're looking for. Take a shot. I'll give you a few minutes to struggle. Or succeed. What's the line for homecoming again? What's the line? 7-point favorite? That's what I figured out too. We're ranked higher than Duquesne, and if we look at the saving rate, we're 4 points higher. Plus you get 3 for being home. So 7-point favorite. I can't. My son has a game at Shade. So I would like to come. Especially this is a big year for me. This is a 25th anniversary something. It's homecoming. What are you laughing at, Malik? Huh? In 1991, I was the homecoming king. You guys know that? Yeah. What do you mean? You don't believe that, Sydney?
No, I didn't.
You're like looking at me like, how could he have been homecoming king, right? So it's the 25th year. I thought they'd invite me back, right, to crown the king, but they didn't. Yeah. It's a kind of a bittersweet thing, though, because this is a true story. I had a crush on the queen, like for years, like 2 years probably, right? But I never asked her out. Never asked her out. But I was named king and she was named queen, so that's that's kind of a confidence boost, right? So I asked her out like after the ceremony, and You know, I'd rather just put her, told me, no, I'm not interested in you. But, she, you know, it's a Saturday. She tells me, I have a big exam on Thursday. That was why she wouldn't get involved in that. And this is the worst thing, she was an elementary ed. It wasn't like she was like, you know, pre-med or anything like that, you know. So I'd just rather her say no, you know. True story. I went out and had a good time. I'd rather just hear no, you know. All right, so let's do this, right? An aerospace company has submitted bids on 2 separate defense contracts. The company president believes that there is a 40% probability of winning the first contract. If they win the first contract, the probability of winning the second is 70%. However, if they lose the first contract, the probability of winning the second decreases to 50%. So we're going to kind of handle this one at a time. So I'm always going to ask you to define the events. What are the events? Tell me what the events are. What are the events? What contract, though? I'm going to say W. Let's do this. I'm going to say F is win first contract. And we'll say F complement is lose first contract. We'll say S is win second contract. And S complement is lose second contract. Okay, so we defined our events. And I don't care, you guys are going to use W and L. As long as you know that there's a first contract and a second contract, win and lose. You could have done that. Now I want to draw my tree. So what goes first on my tree? That's sometimes the hardest thing to figure out. What goes first on my tree? What happens first? First contract, very good. So there's only 2 things that can happen with the first contract, right, Mr. Boyd? We either win it or we lose it. And I think it tells us the odds of winning the first contract is 40%. It doesn't tell us the odds of not winning it, but we can deduce that via the complement rule. If there's a 40% chance we win the first contract, 60% chance. This has to add to 1. Okay, very good. Now, let's read that next sentence. It says, if they win the first contract. So where are we at in the tree? If they win the first contract, where are we at? We're up here, okay? If they win the first contract, so given that we win the first contract, the probability of winning the second is 70%. So then what's the probability that we lose the second contract given that we won the first? 30%. Very good. Let's go down here. What has happened if we're right here? Well, yeah, but we've lost the first contract, right? And if we lost the first contract, the probability of winning the second, Mr. Boyd is right, is 50%. So the probability of losing the second is also 50%. So I've created the tree. There's 4 possible outcomes, right? Because there's 4 ends of this tree. Win-win, win-lose, lose-win, lose-lose, right? Those are the 4 outcomes. It's asking me, what is the probability they win both contracts? So that's probability of S and F, win the first and the second. What do I have to do to find the probability they win both contracts? Multiply along the path where that happens. 40% times 70%, there's a 28% chance that when we're done with this, they win both contracts. Does that make sense? What is the probability they lose both contracts? That's the path I don't want to take. Where's that path? Boom, 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 boom. 60% times 50%, there's a 30% chance we lose both contracts. What is the probability that they win only one? It didn't say, it doesn't care if it's the first or the second. There's two outcomes where we win one contract, there and there. 40% times 30% is 12%. 60% times 50% is 30%. Add those up because I won them both, and there's a 42% chance that I win one. Does that make sense? Let's have you guys do one more. I'm going to run to my office and get something. Do 13. Define the events, draw the tree, figure out what they're looking for. Watch the final debate. It was better. It was more decorum than the first two, I thought. I thought the moderator did a really nice job.
The guy I was watching it with was he was saying how Hillary says it's all about the children. And he's like, no, watch right here. It's all about the children. And then literally the next sentence was like, it's all about children.
Yeah, they do have. They were well prepared. They have good canned lines. All right. So what are the events here? What are the events that I'm going to define? Define our events. That's the first thing. All right. So I'm not going to write it out, but we'll say D, R, and O. Okay? D, R, and O are events. So I randomly make the first selection. We have Democrat, Republican, and other. So we have actually three branches of that first pick, right? Democrat, Republican, and other. The odds that someone is a Democrat is 44%. The odds that they're a Republican is 37%, and another, which I think we refer to as independent, is 19%. Okay, so 44, 37, and 19. Okay, that's the first pick. The second pick, if I've picked a Democrat, the second pick could also be Democrat, Republican, or other. So the probability that I choose a Democrat, given that I just chose a Democrat, is 44%. The probability that I choose a Republican, given that I just chose a Democrat, is 37%. The probability that I choose an other, given that I just chose a Democrat, is 19%. Okay? I would have the same thing here. And I'm not going to write it all out, but we'll say 44, 37, and 19. You guys get it? Democrat, Republican, other. Democrat, Republican, other, 44, 37, 19. Now let's see what it's looking for. It says, if two registered voters are selected at random, what is the probability that both of them have the same affiliation? So we want to know what's the odds that we get Democrat, Democrat, or Republican, Republican, or other, other. So how many outcomes total are there here? 9, because there's 9 ends of the tree. We're only concerned with this one, and this one, right? Democrat, Democrat, Republican, Republican, other, other. So all I need to do to figure those out, let's see, 44% times 44% gives me 19.36%. 37% times 37% gives me 0.1369. And finally, 19% times 19% gives me 0.0361. Okay? That's Democrat, Democrat, Republican, Republican, other, other. I add those three together, 0.1936 plus 0.1369, and I get roughly 36.6% of the time I'll pull two that are the same party affiliation. So you guys see how this tool can help us take, we could have multiple branches of the tree. We have 9 outcomes here. If I chose a third voter, what would happen? Well, now, hell, it kind of explodes. Now I have, 3, 3, 3, 3. I'd end up with, 27 outcomes, right? And if I did it again, I'd end up with 81 outcomes. So I'm not going to give you any homework that takes that many outcomes, but that tree can really help us figure out results. All right, here's what I would like you to do for homework. I'd like you to do number 12. And then 15 through 18. Okay, 12 and then 15 through 18. I got this out of my office, so you guys didn't believe me. Oh, it's very old. Can you see me? That's me. 25 years ago. See how much hair I had? But I look the same, don't I? Have a great weekend. Malik, I want to see you after class. And Jordan, I want to see you.